under the stereoisomerism, the second type is a geometric isomerism. Coming to the requirement when this geometric isomerism comes. As I said, whenever a carbon-carbon is attached with single bond, the bond is liable to rotate. But whenever we have a double bond, two bonds are there, just like two wooden pieces are attached through the two nails, then the rotation is blocked, isn't it? Like that here also, when two carbons are attached with one sigma bond in addition to the another bond, pi bond, rotation will not take place. That means conformational isomerism ends there only. So, we get a new type of isomerism, that is called geometric isomerism. So, first requirement is presence of double bond, so that the rotation is not going to stop. So, this is the first requirement, presence of the CC double bond. Second one is, it is not only the CC double bond, but you must have some groups. What type of groups means, if first one is A, the second one should not be the A, it can be B, okay, but not A. Here you can have the same A and B once again. This is the one type of the arrangement. The second time you can have a, here if it is A, this can be B. A is same repeated, but you can have another group C. That means A is repeated, B is not repeated. This is second type of eligibility. Third one is if A is there, let us have a B, here a new group C, again D. All the four are different, isn't it? A repeated, B repeated, A repeated, B is not repeated, A is not repeated, B is also, all the four are different. But either side non-equality, that is A should not be B, A should not be B, A should not be equals to the A should not be equals to the B. So, both the sides non-equality should be there. Unidentical groups on the both the sides is a must. One side if A is repeated or B is repeated, any group repetition on one of the side will become non-eligible to the comp. Say A, not A, A, not A, isn't it? On the both the sides, unidentical group. However, we have an exception. Even cyclo compounds also will have this type of the algebra. Even cyclo compounds means cyclopropane, cyclobutane, cyclopentane, and so on, also going to show this type of the cis and trans type of the isomerism that will deal later. But these two eligibilities, that is possessing a double bond, having non-equal or unidentical type of the groups is the eligibility. According to that, we have the first eligible compound, one methyl, one hydrogen, right? This is the first type, one methyl repeated, hydrogen repeated. One methyl, one hydrogen. This side, let us have a hydrogen common, but it is ethyl. So, this side different, that is also different. You can have a one methyl, one hydrogen, one ethyl C2H5, one propyl C3H7. All four is different, right? So, all the four different, you can have A, B, C, D type, or AB, AC, or AB, AB type. All these types of alkenes are eligible to show the geometric isomerism. This is called what? A requirement eligibility, on which questions are coming. I will give 3-4 types of the compounds and ask which of the following can show the geometric isomerism. Like for example, 1 butene is there, 2 butene is there, isobutene is there, and the butene something like this. Of all these four, which can show geometric isomerism means in the middle one, if you carefully observe, there are two more hydrogens, right? So, hydrogen methyl not identical, hydrogen methyl not identical. Here you have identical groups, two hydrogen same, therefore gone. This is not having that repeatability is not there. Two methyls are same, two methyls same, so gone. Two hydrogens also same, twice it is not eligible. So, here also two methyls are there, one is hydrogen, okay, but one is there, this side also methyl you can take. So, both the sides methyl, methyls not eligible, okay. So, both the sides you must have a non-repeatable groups, then you will get this eligibility. So, except these two, all are not eligible for the geometric isomerism. So, let us see specific example that taking that non-repeatable groups and how it differs in the property C. Let us take the 2-butene. The 2-butene can be two types. 2 methyls only same side, one compound, and 1 methyl is up, 1 methyl is down. Both are 2-butenes. If this methyl is that side, that is no more 2-butene, isn't it? Both are 2-butene. Order is same, methyl, carbon, double bond, double. So, order is same, they are not structural isomers. Only the groups arrangement in space is different, just like in the conformational also, groups are rotating in space different. So, the groups arrangement in space is different, that is why they are stereo. Under that, they are in plane, the molecule is in plane. So, in the plane, if the groups right side, left side, then geometry, it is called. So, double bonded compounds are showing here. This compound is called, both are same side, it is called cis 2-butene. The opposite 2-butene is called trans 2-butene. The cis and trans refers the same side and the opposite side, right. Now, in the cis 2-butene, the distance between the two methyls will be less. Less distance means more repulsion. So, the consequent of this 2 methyl same side, isn't it? Same side methyl gives the more repulsion. More repulsion means less stability. Less stability means more potential energy. Therefore, when you burn it also, you will get the more heat of combustion. What is called heat of combustion? When the molecule is totally burnt into carbon dioxide, and when you burn with oxygen, it gives the 4 carbons means 4 the carbon dioxide plus 6 plus 2 8 means 4 H2O molecules plus some energy. So, there also it gives the 4 carbon dioxide 4 H2O, but the energy will be different. This is having higher potential energy, therefore, more energy is liberated, here less energy. So, because of the heat of combustion is different, we are considering these two as isomers. Their molecular formula is same, but the properties are different. Which property means we recognized that the more heat of combustion. So, this is the one property. It is not one property. We can have more properties. Let us have study some what are the other properties means. When this compound is treated with hydrogen in presence of a catalyst like nickel, it gives a N-butane. In fact, this also gives the same compound, but if you see the potential energy diagram, the 2-butene will have a higher potential energy, right. Trans-butene will have a lower potential energy. Both are alkenes, right, potential energies are different, but when they are hydrogenated, both gives the N-butane. So, one gives the less energy, another one will give the more energy when converted into the N-butane. Both are converted to N-butane. So, this is this side if you take as a potential energy on the y-axis, this side you take the progress or the coordination, this coordinate is taken as a reaction, unreacted, reacted product. This side reaction we are showing on the x-axis, potential energy on the y-axis. This is called energy profile diagram of the heat of hydrogenation. We are not burnt, we have just converted into the N-butane. So, N-butane is formed with some liberation. So, here the less energy is liberated, here the more energy liberated. Unstable compounds are higher potential energy when converted to N-butane, which is common in this one also. So, less potential energy will give less energy, more potential energy, more. This is called what? The heat of hydrogenation, heat of hydrogenation. when you are adding hydrogen and converting into alkane, alkene is converted to alkane, heat of hydrogenation, all these heats are taken standard as a per mole, not for 1 molecule or 10 molecules. Per mole means Avogadro number of alkenes when converted into Avogadro number of alkanes. By adding a Avogadro number of hydrogen, the heat liberated is called per mole. So, that per mole if you calculate, alkenes with cis will give more energy, trans will give less energy. So, therefore, the heat of combustion is different, heat of hydrogen is also different. Like that, if you go on search the other properties, like when methyl group is attached to the alkane, this is sp2 carbon, this is sp3 carbon. When S percentage is more, it pulls the electrons. This type of polarization of the bond, the methyl group is giving partly electrons to this side, this is also giving this side, net goes this side. This is called bond polarization, this is called polarization on the molecule. The whole molecule acts as a tiny bar containing the delta plus and the delta minus. A molecule develops a delta plus on one side, delta minus on the this side. What happens in this molecule? What happened? It is donating, get cancelled. So, there is no charge accumulation on the molecule like trans. So, the mu, that is dipole moment, is said to be 0 d by units. Here mu will be not equals to the 0, some value will be there, net dipole moment. Here it is cancelled, therefore, that will have almost equals to the 0. So, trans to butene is not polar, cis to butene is having some polarity. Whenever this molecule, so dipole moment values are different. Right, this is another property. When you have a polar, this is having a polarity, therefore, a polar molecules are more soluble in the polar solvents. When I take polar solvent, this is more soluble. Non-polar solvent, that is more soluble, right. Like that, one is attached to the another, another it is attached to another, huge number of properties are going to be different. I am not going to actually enumerate or count what exactly, how many properties are different, because I said even one property is enough. So, therefore, counting the properties are not necessary, but do you have a difference in the polarity? Yes. Cis compounds are more polar. Cis compounds are more polar. More polar means higher boiling points. Intermolecular forces will be when you have another molecule having the minus sign plus charges, they have a more intermolecular attraction. Therefore, cis compounds, whenever they are polar, they have the higher boiling points. Higher boiling point, lower boiling point. However, when you take melting point, the molecule is more symmetric. Trans compound just like a small bent, but this is almost like a U shape. So, the symmetric molecules pack in a crystal. So, instead of lower melting point, it will have a higher melting point. This is an exception. However, in general, lower boiling point molecule will have a lower melting point, that is in general. But we have a just like neopentane. Neopentane will have a less surface area, lower boiling point. But when it comes to the melting point, that is symmetry is more, therefore higher melting point. Like that, here also an exception is there. Trans compound will have a dipole moment 0, non-polarity, therefore lower boiling point. But symmetry is more. This higher melting point is because of the more symmetric. How can you say it is more symmetric? See, there is a small bend, almost looks like a straight chain molecule, whereas here it is a U shape. So, therefore, which is more bent means this is more bent, that is less bent. A straight molecule, just like a chalks, if you take in a box, they pack in a more better way. So, therefore, straight molecules are more packable, or they in a crystal they come to more closure, leaving the less gaps, more van der Waals forces, therefore higher the melting point. So, melting point is high, however, the low boiling point is low. Okay. So, therefore, cis compounds will have a higher boiling point, but low melting point. That is a controversing feature actually. Exception is there, but valid reason is there, therefore, it is also very important. Like this, geometric isomers will have a clear cut groups opposite same side, that makes the molecular formula is same, but the number of properties we are going to observe as a difference. Similar the case, we have a wonderful example in the case of a double bond containing two COOHs same side. Okay, that is called maleic acid. This is called maleic acid. In fact, you can systematically you can call it as a butene dioic acid, specifically second carbon. So, but2ene dioic acid or tubetene dioic acid is called maleic acid, whereas 2COH when they are opposite COOHs means it is called trans 1 or it is called another name, unfortunately, fumaric acid. Generally, the geometric isomers are not given separate names. See, cis and trans, name is same, tubetene, but here common people have got two separate names also. Maleic acid and fumaric acid are geometric isomers having two different names. This is a rare case once again. Geometric isomers having two different names for each one. Maleic acid is a cis one, fumaric acid is a trans one. We have one specific observation. When maleic acid is heated just below the 100 degrees only, it gives anhydride formation. Two OHs lose water and becomes into anhydride with CO and O. This is called maleic anhydride. This type of heating at below 100 degrees, nothing happens in the case of fumaric acid. The reason is not because of the less reactivity or stability and so on, just because of two COHs on the opposite direction. So, on the same side they can make an anhydride formation, opposite side they are not able to make. Therefore, the maleic acid will not give this type of maleic anhydride, but the fumaric acid is giving an anhydride. However, if you heat it very strongly, the pi bond opens and it rotates and makes again a pi bond, then undergoes. Lower than less than 100 degrees, though there is no reaction, but beyond 100 degrees if you heat it, then it gives anhydride, but same anhydride comes. That is what explained. Pi bond opens, because if you give more heat, pi bond opens, and that pi bond after opening it will become single bond and rotates. That means two COH will come on the same side. When they come same side, immediately anhydride is formed, again pi bond is also formed. So, again same maleic anhydride. The question is now, fumaric acid on heating below 100, no reaction because opposite one. However, beyond 100 degrees it gives anhydride, but it gives a maleic anhydride. Fumaric acid giving maleic anhydride. Explain the reason. Means fumaric acid opens the pi bond at higher temperature, becomes a single bond, shows conformation. Two COH when they come same side, immediately water is lost and pi bond is formed. We get a fumaric anhydride. So, we have some specific different type of the even chemical reactions just because of the groups same side and opposite side. So, the argument of same side opposite side will not come into the higher reactivity, but just the geometrically the groups are arranged in a different way, therefore, they are showing the properties also different. We do have cyclo compounds having the group same side and opposite side. There also we have this type of discussion, but the geometric isomerism, best example tubetene, little higher example the maleic and the fumaric acid.